Hello, I'm Matt Leftwich. I'm the President and Engineering Director at Nanomatronix, and I'm here to present our AEDC Phase 2 SBIR matching application for the efficient neuromorphic processor design for autonomous space operation. I'm going to present a brief corporate overview, then an overview of our microelectronics SBU, our Phase 2 project overview, the key innovations, the project objectives, Phase 2 outcomes and anticipated Phase 3 objectives, the need for AEDC matching, and the long-term commercialization model.
I founded Nanomatronix in 2005 to serve as a technology transfer pathway for my master's work and PhD work, both in microelectronics packaging and carbon nanotube synthesis and integration into microelectronics, or more specifically thin film devices. So the integration of nanomaterials in microelectronics, so to speak. In 1999 to 2012, I was overburdened with consulting work to Space Photonics, and they basically hired me as a direct leased employee to serve as the chief operating officer for that company. I generated close to 20 million in funding for them, and we had developed quite a few projects or products with quite a few successes, etc. Then from 2011 to 2013, I was contracted through Nanomatronix. I finally began to put more focus into Nanomatronix as a product development business as opposed to a consulting business. And we were contracted to conduct a large BGA solder ball reliability study for multiple patent infringement cases. In 2012 to 2015, we won a NASA Phase 1 SBIR for the continuation of my PhD work, which was ultra-long carbon nanotube synthesis. We did not win the Phase 2. They were not willing to fund the procurement of the PECVD reactor that we had simulated and modeled in the Phase 1. So we sought Arkansas TDP funds. So we received those funds. We built the reactor. The reactor is in place and in operation today, and we have received DOE funds, SBIR funds, to continue that work. So that work is pushing forward. In 2015 to 2017, we developed a current, more aggressive business strategy for Nanomatronix, which was the inclusion of a nanotechnology and biotechnology strategic business unit, in addition to what we were doing in the microelectronics realm. In 2017 to 2018, here we are today with full implementation of the above strategy. It's led to the creation of what's really a technology transfer and commercialization consortium. So we've increased research institution collaboration with University of Arkansas at Little Rock, UAMS, also TAMU and UC Davis and UMass Lowell. For various types of projects. It's increased momentum in all three of our SBUs. We have several new awards, 3 new SBIRs, and a couple of large subcontracts through government primes for qualification of some space electronics. We've also have some new patenting and licensing activity that's resulting in some interesting activity overseas, and then several new opportunities for requests for proposals, bids, and quotes going forward. To the tune of around 5.2 million over the next 2 to 3 years that has been awarded. And with significant follow-on expected after the majority of those contracts as well. So this particular project, this particular SBIR project, falls underneath our microelectronics strategic business unit because it is for the development of asynchronous integrated circuits. They have application in radiation, heavy radiation environments, cryogenic environments, and in some cases with slight design variations, high temperature environments. So in general, the asynchronous architectures are ideal for harsh environments. And when it's oftentimes coupled with a clock generating circuit or a synchronous circuit or digital circuit that could operate in those temperatures as well. Which is why we're studying the particular fabrication techniques and process that we are, which is a 90 nanometer TSMC process through Moses. Anyway, we'll get to that in a moment. But the core technologies and services that we offer through our microelectronics SBU include quite a few things, and you see a large variety of them here, images of hardware that we've produced, as in some cases we've produced in-house, and in other cases we've produced as consultants for our customers. We have developed quite a few harsh environment microelectronics devices for high-speed communications and interesting anti-tamper applications and X-ray blocking applications and things of that nature. But quite a bit of experience, quite a bit of capability and expertise in regards to the development of harsh environment hybrid microelectronics, which again, several examples that you see here and then I won't read verbatim. You guys can certainly take a look at that and read it. NASA's primary objectives for this Phase 1 SBIR project are to develop neuromorphic processing software, hardware, algorithms, architectures, simulators, and techniques as enabling capability for autonomous space operations. They're also focused on innovations that provide lower SWaP, or lower size, weight, and power, applications suitable for lunar orbital or surface operations. Therefore, the Nanomatronix, University of Arkansas, and Duke University team propose to develop key enabling techniques for designing an efficient and robust ReRAM-based neuromorphic processor at the circuit, architecture, and algorithm levels, and to explore systematic approaches of vertically integrating these techniques through interactive cross-layer optimization. Compared to the existing work and/or state-of-the-art in industry, the proposed ReRAM-based neuromorphic processor design technique has the following significant improvements: a more efficient and robust circuit implementation, processing in memory or PIM architecture, algorithm optimization with a focus on quantization and robustness enhancement, and system integration and evaluation.
And therefore, the following Phase 2 objectives fall out: the demonstration of a complete architecture design consisting of multiple ReRAM-based processing elements, a complete data mapping and data management scheme for high efficiency, the algorithm optimization flow dedicatedly optimized for the ReRAM-based neuromorphic processor, a complete design frame for efficient and robust ReRAM-based neuromorphic processor, and finally, a full system hardware implementation for function demonstration and performance evaluation. The second objective will be to complete environmental screening on a variety of those test chips to confirm that they're compliant with the necessary environment, especially radiation, for including total ionizing dose and single event effects for both proton and heavy ion radiation. And then the third objective is to identify and pursue Phase 3 opportunities within NASA and other federal programs. We anticipate the following Phase 2 outcomes, and that's a complete ReRAM-based processing element design with high power efficiency, and asynchronous network-on-chip architecture for interconnecting multiple processing elements and providing memory access in an efficient manner. A fine-grained quantization model and implementation further improve the efficiency. A test chip for early evaluation of key circuit components in silicon. Actually, it'll be a CMOS process, and then our anticipated Phase 3 objectives will be the completion of the full architecture design consisting of multiple ReRAM-based processing elements, complete data mapping and data management scheme for the higher efficiency, algorithm optimization flow and with optimization dedicated for the ReRAM-based neuromorphic processor, a complete design frame for efficient, robust ReRAM-based neuromorphic processing, a full system hardware implementation for function demonstration and performance. The Phase 2 matching requested will allow us to complete the fully functional chip tape out and packaging of our second pass chip. And we'll use about 25K of the match for that. We'll also fabricate our 512 by 512 memristor crossbar array, and that'll take about 25K of the ADEC match. Again, in both of those cases, the ADEC match is providing 50% of that cost, and the other 50% of that cost, or other 25K of those costs, are being provided by our internal R&D funds. And then the third need is to increase basically Phase 3 investment probability while also retaining a couple of jobs critical to the continuation of the project. So it'll partially support the retention of one employee and two part-time employees through the Phase 2 to Phase 3 transition, and then the two part-time employees will transition to full-time upon Phase 3 continuation. Without this match, we'll not be able to produce the fully functional NMP by the end of the Phase 2 project. And that conclusion would then depend on the Phase 2E funding and or Phase 3 investment reduces the chances of Phase 2 transition success.
So from the long-term commercialization perspective, we intend to license and or patent the asynchronous design architectures and ReRAM design architecture for custom ASIC product development, production, and sales. Some of the IP, there is existing IP involved here that is owned by the University of Arkansas and is already being licensed by Nanomatronix. There's some existing IP being brought to the table from Duke that will also be licensed accordingly. And then there will be joint IP developed among us three as a result of this project. So new IP will be developed and leveraged as well, and the relevant pieces will be licensed accordingly. A related patent is also being filed or has been filed by myself and Dr. D and actually Dr. Zhong Chen from the University of Arkansas for stacked circuitry monolithic stacking, that is, not physical stacking, but monolithic stacking to reduce power and make a more power efficient device from the ASIC design perspective. Additional SBIR ST2 proposals will be prepared and submitted for the development of related ASIC prototypes and products. We anticipate ramping up design and production services in Northwest Arkansas. We have recently hired 4 new part-time employees for this project. The momentum that we have created with our microelectronics strategic SBU, our strategic business unit, and the momentum that is being created for the other 2 SBUs is really getting very exciting. The company has a lot of potential and a lot of momentum, and we anticipate that momentum and growth continuing to expand. Thank you for your time. Thank you for viewing the presentation, and we look forward to continuing to work with the Arkansas Economic Development Commission.